Hello and welcome to the Mind Grid. And today we are talking about quantum beginnings. Well, quantum computers are the craze today, and billions of dollars are being spent in trying to make these groundbreaking computers. But do you know that the field of quantum mechanics started with a very simple experiment gone wrong? It all started when classical physics predicted a catastrophe, that a simple heated object should emit infinite lethal ultraviolet radiation. This mathematical breakdown, called the ultraviolet catastrophe, proved that the laws of Newton-Maxwell were fundamentally broken. To save reality, Max Planck proposed that energy isn't a continuous flow, but travels in discrete quanta. With that single radical step, the classical era had ended and quantum mechanics was born. So now, let's walk this yellow brick road and look at how all this came about. Alright, so let's look at some of the scientists that helped blaze the trail for the blackbody radiation. In 1791, Pierre Prévost put forth a preliminary theory of radiative heat. Following that, in 1830, Melloni made a thermopile device to convert thermal energy to electrical current. In 1847, John Draper introduced Draper point, which is the temperature at which emitted radiation becomes visible. In 1858, Balfour Stewart measured radiation using thermopile, and compared to lampblack, Stewart had found a close approximation of blackbody. In 1859, Gustav Kirchhoff introduced his law of thermal radiation. In 1860, he formally introduced blackbody as idealized object that absorbs all incident radiation. In 1879, Joseph Stephan empirically described dependence of temperature on total energy emitted by blackbody. Now, Stephan's work is empirical, so in 1884, 5 years later, Boltzmann actually proved Stephan's law using thermodynamic arguments. Then in 1890, Wien used thermodynamics to show wavelength of peak radiation is inversely proportional to absolute temperature of body. In 1896, Wien also attempted to describe the entire spectrum of blackbody radiation. Finally, in 1911, Wien was awarded the Nobel Prize for his work on laws governing radiation of heat. Wien was a professor of experimental physics at University of Munich. He was a strict examiner who insisted even theoretical physicists be well versed in lab work, and he famously nearly failed Werner Heisenberg on his doctoral exam because Heisenberg lacked experimental knowledge. In 1896 paper, Wien derived his distribution law by drawing an analogy between thermal radiation and kinetic theory of gases, hypothesizing that radiation is emitted by molecular vibrations. He applied Maxwell-Boltzmann's distribution, which described the number of gas molecules at a given speed for a temperature, thus incorporating the exponential term e to the power minus v square to related velocity, frequency, and temperature. Wien achieved remarkable success accidentally, applying classical gas kinetics to a problem that requires quantum mechanics. Wien had correctly identified the tail at high frequencies. However, Wien's law broke down in infrared regions, as proved by Otto Luemer and Ernst Pringsheim. Building on the earlier works of Wien, the Rayleigh-Jeans law emerged through the efforts of British physicist Lord Rayleigh and Sir James Jeans between 1900 and 1905. Lord Rayleigh first derived the relationship in June 1900 by applying classical statistical mechanics, specifically the equipartition theorem, to the electromagnetic standing waves in a cavity. He treated these waves as oscillators that each possessed an average energy proportional to the temperature. In 1905, James Jeans refined this derivation by correcting a numerical constant, resulting in the final formula used today to describe blackbody radiation at long wavelengths. This classical theory set the stage for Max Planck by exposing a fundamental crisis known as the ultraviolet catastrophe. While Wien's law worked well for high frequencies but failed at low ones, Rayleigh-Jean's law did the opposite. It was accurate for low frequencies, infrared for example, but predicted that as the frequency increased towards the ultraviolet, the energy emitted would become infinite. The reason for this was that, according to Rayleigh and Jean hypothesis, there would be more modes of vibration, each carrying the energy kT, and as there were infinite number of modes of vibration at high frequencies, the resulting energy would also be infinite. This glaring contradiction with experimental reality proved that classical physics was incomplete. To resolve this catastrophe, Max Planck was then forced to abandon this classical assumption of continuous energy and propose a completely new way of thinking. Although, at this point, this is not a wave-particle debate, but Wien's law successfully described the high-frequency short wavelength end of the curve using assumptions mirroring particle behavior. Rayleigh-Jean's law matched the low-frequency long wavelength end based on more of a classical wave mechanics. Max Planck, therefore, now had to resolve this by proposing a quanta of some sort demonstrating light's dual nature, being able to do both sides of the equation. Now we can see that Planck had a brilliant idea that to fix the ultraviolet catastrophe, there must exist some barrier to distributing the Boltzmann energy to all possible modes of vibration. Some of these modes will just not be excited as their quanta are just too big for the energy going into them and thus get rejected. This idea played really well and unified the thermal spectrum conjecture of Wien and Rayleigh-Jeans. At low frequency, this quanta is readily available, but there are fewer and fewer modes just like Rayleigh-Jeans predicted. These modes don't fit within the harmonic oscillator. At high frequency, the number of modes explodes and there are too many modes available, too many frequency modes available to absorb the Boltzmann energy. However, the quantum nature of light rejects these modes because the quanta are big and expensive and radiation falls off exponentially. Planck was awarded the Nobel Prize in 1918 for his discovery of quanta of energy as a fundamental contribution to a new branch of physics. Planck was not 100% committed to the idea that light itself had a quantum nature. It was a mysterious mathematical trick to explain the graphs he had observed. It was only Einstein that affirmed the idea that light was indeed quantized, and he published his work in 1905 on the photoelectric effect. Einstein borrowed Planck's light quantum idea explaining each substance has its own threshold of energy W, and the electrons are trapped when their energy is below W. When the light with the energy of photons above W falls on the substance, electrons can be emitted, each with the energy E minus W. Einstein, who never received the Nobel Prize for Theory of Relativity, did win in 1922 the Nobel Prize for Physics on his work on photoelectric effect. Though Einstein never liked the idea of nature being quantized, but it was his explanation and the work of Planck that pioneered the quantum revolution. So we come to the end of this interesting story that saw 3 Nobel Prizes, dozens of brilliant minds coming together to solve the mystery today we call the ultraviolet catastrophe. I hope you liked the video, and if you did, please like and subscribe to my channel, and I'll see you in another video. Until then, take care and bye-bye.